Hello, and first let me start by thanking everybody who is attending our webinar today. This webinar is sponsored by Triphase Automation and is focused on Cognex's new and exciting technology, deep learning for machine vision applications. My name is Eric McKibben. I am the product manager with Triphase Automation for Cognex. And I've been working with machine vision for almost 20 years. And in those 20 years, I've seen a lot of new advancements in terms of hardware, in terms of software, algorithms, but nothing that's really as potentially revolutionary as deep learning. With hardware that is improving CPU processing power, is enabling advancements that haven't been seen. Nothing since 1995, when Cognex introduced their PatMax technology as the first geometric pattern matching tool, has anything really created this kind of buzz or paradigm shift in the industry. PatMax was something that brought a lot of power to machine vision applications, made it a lot easier to find the parts, which just really made programming simpler and more reliable. Now with deep learning, we're seeing a real paradigm shift in the industry. The emergence of low-cost, high-performance graphic processors or GPUs has enabled a transition in our industry where the academic theories of artificial intelligence can now be implemented in a cost-effective way to solve previously unsolvable solutions. So first, we'll talk a little bit about the agenda for the presentation. I suspect many of you are familiar with Triphase and or Cognex, but for those who aren't, I'll give you a brief overview. But the focus will be on the basic principles of deep learning technology, how it works, but on a practical level. Next, we'll give you a sense of where to target deep learning technology. And here we want to emphasize that as revolutionary and exciting as it is, it's not a catch-all, and it should be thought of as another tool in your toolbox for machine vision. Deep learning is not intended to replace that full spectrum of tools or traditional tools that exist. It's a complementary technology. We'll conclude with a few words of advice on what you, as a user, need to consider in order to successfully deploy deep learning solutions. If you have questions during the presentation, I've muted everybody. Please chat them in. We'll take a break about halfway through to answer some of those and take some time at the end of it to answer any more that may come in. So first, who is Triphase? We've been in business in covering Wisconsin and Northern Illinois for over 27 years. All of our sales and support staff are degreed engineers, either electrical or mechanical or computer science, meaning that everything that we sell, we provide, we know how to implement it, we know how to program it, we know how to make it work. And we carry an extremely broad line of suppliers, some of industry leaders that are doing a lot of great and fascinating things with technology and kind of pushing the industry forward. And with all of these great and powerful suppliers that we have, we also add some value add services, whether it's programming, kitting, assembling, and part of that is through our Innovative Technical Services Division, or ITech. But who is Cognex? Cognex has been a leader in the machine vision industry for nearly 40 years, over 2,300 employees worldwide. The most important number to really pay attention to on the slide is the one in the lower right-hand corner, the 2 million plus systems shipped. In 38 years, it's 2 million, but really from 1982 to 2014, it took that long to ship the first million. So in the last less than 6 years, they've shipped the next million, which that just points to how evident machine vision is and how mainstream it is in the technology industry or in machine and factory automation to help manufacturing plants kind of move forward. But what's driving that kind of demand? It's not really talking industries or necessarily technologies, but kind of the buzzwords that are driving industry right now. So logistics, how do we get parts from one place to the next? How do we manage all of that? Deep learning, which we're here to discuss. 3D, three-dimensional vision is another kind of paradigm shift in machine vision. And the Industry 4.0, how do we get more information out of our machines, out of our factory floor? So looking at the picture you see on the screen now, you may have seen something like this, or at least on a smaller scale. But today there are literally hundreds of millions of people doing things with their eyes and brains in manufacturing. And an estimated 35 million people are doing quality control tasks, picking up parts, looking at them, determining whether they're good or bad, just using their eyes. In many cases, this isn't simply a cost consideration. It's because some inspection tasks are extremely difficult to automate, and people just do them better. The problem is they just can't do them very consistently for very long. If you're picking up a part and looking at it and trying to find a small defect, you may do that really well for an hour at a time, 2 hours at a time, 4 hours at a time if you're really good and diligent. But you can't maintain that 5 hour or 8 hours a day, 5 days a week. So today, with the emergence of deep learning technology, many of these visual inspection tasks are transitioning to the domain of automated machine vision. So what is deep learning? If we think about how humans learn, we don't teach a child to draw a house by listing a long set of rules on how to draw a house. Granted, all kids probably draw the same house you see in her thought bubble of, one door, one house, and a roof. But when trying to discern what is a house in the real world, you don't list a set of rules saying, a house has 4 walls, 8 windows, 2 stories, because those rules break down really quickly in the real world. Instead, we teach the child, and by example, showing them what enough houses look like so that they learn what they look like. And when needed, we give feedback when there are confusing cases. Now, there are companies out there like Google and Microsoft that are using deep learning and artificial intelligence to do some of what we're talking about, identifying a house, identifying a cat. If you go to Google and search for an image of a cat, you'll get thousands of pictures of a cat. But they're using massive server farms, hours and hours of computer science majors programming those type of things. And even they don't get it 100% right all the time. So if I was in a room with everybody doing this presentation live, I would ask people to kind of give me some concepts rather than rules that define a house. And you probably usually provide, attributes in a generic sense. A house has a roof. It's made of bricks or wood. They have windows, doors, a yard, a driveway, some less stringent criteria, but still more or less rules-based. However, are any of these images of houses? They're not. And even though they share several attributes with that of a house, our brains, and even that of that young child, can tell them apart. So how exactly can we train a computer to tell them apart? We do it with deep learning technology. So deep learning, really, it's a specialized subset of artificial intelligence. And we've all heard of artificial intelligence. AI, at a basic level, is a machine doing something that a human can do that is more than just strict repetition. Pattern recognition is an example of AI. We tell the vision system what to look for, and it finds it, and what makes it AI is that it can adapt to changes when the pattern doesn't precisely match the original model. The pattern could be larger, rotated, even missing features, but vision tools like PatMax can handle these variations. But PatMax does not improve its performance over time when exposed to more images. We train it on a single image, it learns what the pattern looks like, and it goes and looks for that pattern every single time. Machine learning is a class of AI using algorithms that improve over time when exposed to new data. So as if you were to look at real machine learning, as things change in your machine, as more information is provided, there's a lot of data analytics that go into it to determine what is going on, how to improve with things that are going on. But if we look at the example on the screen, in this example, we've given the computer some basic parameters that describe a car versus a truck. When the computer encounters a parameter it hasn't seen before, it can make a reasonable prediction of the vehicle type. In this case, the first 4 lines in the table include the vehicle type, and the algorithm uses a combination of the weight and length to create bounds for the categories. Now, when a new piece of data arrives, the machine makes a judgment to categorize it and includes the new result in future classifications. Voice recognition software is a great example of machine learning. As more people speak to the software, the more times you tell Siri, "Hey Siri," the better it learns what you're saying. It learns those common words and phrases. Deep learning, though, is a little bit different than machine vision. Deep learning employs an artificial neural network that behaves more like the human brain and that it creates associations between nodes that formulate the means of producing an outcome, but it doesn't learn as it goes. You train it, and in that training process, it learns based on the input parameters that you give what the output should be. But as it acquires new images, it's not learning on its own. It requires your intervention to learn more features and more defects. Now, using deep learning to solve a machine vision application requires a little bit of a shift in how we think and our problem solving. We've traditionally relied on application engineers, machine vision programmers who understand how to hand tune or manually tune parameters for dozens of different vision tools using a small set of images. So the PatMax example again, we have one image we train and we go and find that pattern each and every time. PatMax operates by running a very complex and dedicated algorithm, and relatively speaking, has only a few parameters to optimize its performance. With deep learning, we need to think more like a data scientist. We only need to master a few relatively simple tools because a neural network is very generic. It can solve different problems depending on how it is trained. But the key to success is data collection and organization, which we'll talk a little bit more about in a few minutes. The takeaway here is what we need to avoid the typical reflex of a machine vision engineer, who when first exposed to deep learning, wants to start tuning parameters based on a small set of images, 5 images, 10 images. Focusing on, rather than that, we need to focus on the collection of images of a large data set. So the basics behind the deep learning is really the neural network. And for that neural network to work, it first must be trained, which is analogous to the example of the child learning to draw pictures of a house. In this sample view of a neural network, there are input nodes, internal processing nodes, and a single output node. To train the network, we pass information, then a bunch of processing occurs in the middle, which we don't know all of what that is, or we don't anyways, and finally the network generates an outcome. If we simply want to decide between good and bad or presence and absence, the network will provide an output of either there or not there, on or off. For the training to work, there's a very important step though. We absolutely must collect enough images and we must classify all of those images in advance in order to tell the network what answer to expect. So when we're passing that training information in, we have to know what's good. We have to know what's bad. We have to know what is what. We have to know it's a house and not an apartment. We need to do this because the way neural networks work is that for all intents and purposes, each node starts out with a randomized internal coefficient in some version of the complex formula shown at the bottom. And they learn to produce the right answer by trial and error, optimizing those coefficients at each node over multiple iterations until the output matches the specified input. Once the network is trained, we can feed it new images containing houses and images of other buildings that it's never seen before, and it will correctly classify each image. And just a subtle note here, Unlike machine learning, which will improve performance when exposed to new data, once trained, deep learning performance will not change over time. If we aren't classifying or deciding images correctly, that's usually a sign of insufficient representation of the problem you're trying to solve. Or maybe some of the training parameters do need to be adjusted, but there's only a few of them. In order to improve the performance, you need to rerun the entire training process, making sure that your images and your defects are classified correctly and potentially adding in more defects as you find them. If we want to use a neural network for something more than just pass or fail, presence or absence, something like optical character recognition or OCR, we simply need to expand the number of output nodes. Just like in the house example, the network needs to learn characteristics of each letter and number, and to do this, you are required to label every image in advance with the characters present in the image. As each character of each image is learned, nodes in the network activate and an output is produced. Here, since the network is initially being trained, it predictably produced the wrong output. So the result is sent back in what's called backpropagation, where the coefficients at each node are adjusted and the process is repeated until the correct output is produced. Typically, this might take more than 50 iterations using each image in the input set. You can probably imagine this could take quite some time, and you'd be right. So training a neural network requires a PC or laptop equipped with a pretty powerful GPU, or graphics processing unit, in order to complete the training in a reasonable amount of time. So we're going to take a quick break for questions here. And I see one question that came in was asking if there are options for continual training, such as maintaining a small percentage of human inspectors that could keep feeding back data. Say you have a process where you don't know most expected results at training and can only feed it examples you know today. And that is absolutely true. One of the things that you'll learn or we'll discuss with deep learning, it's only going to classify those defects that you train it on. So if there are new defects that are coming up, there's a potential that deep learning may catch those. But typically, it's not unusual to continue to manually inspect those parts for a short period of time, just to make sure that the deep learning is working, and to make sure that we have those images of additional defects or more data to feed into the system to keep retraining it and making the process better. Are there any other questions? All right then, if there's no other questions, we will continue. So the big players in deep learning like Google, IBM, and Amazon, they require millions of images for training. Fortunately for them, these images are out there. They can get them pretty easily. Through the wonders of social media, people who post images and label them as, hey, look at the cute cat. Companies like Google mined these sites and this data, and coupled with massive server farms, they process millions and millions of images. So when you do that Google search, you actually get a cat. Now, granted, it's not always 100% accurate, but there's a lot of variability in what a cat looks like. Cognex Vidi software and their deep learning brings that world to the factory floor by enabling deep learning applications using far fewer images in a GPU-equipped computer instead of a massive server farm. It won't process your images in just a millisecond, but we'll talk about that in a few minutes. Earlier, I said deep learning should be viewed as a new tool in your toolbox. On the left are examples where using traditional machine vision tools are still the best choice. Deep learning doesn't read barcodes. It's not meant for precision measurement or alignment. Most robotic guidance applications won't be able to use traditional or deep learning. There are plenty of OCR applications where tools like OCR Max from Cognex are perfectly acceptable. For well-formed characters or well-printed characters, OCR Max is still going to run faster than deep learning, but deep learning and the Cognex Vision Suite is going to be able to process and recognize characters that OCR Max and may not be able to. So we may not be able to run as fast, but we'll be able to read more of them. The three primary applications for deep learning are assembly verification, defect detection, and challenging OCR. I'll add that I was really skeptical when I heard about the OCR, deep learning OCR, and what it was able to do. Having done enough applications with that, I knew how challenging they were. I didn't buy into it until I started seeing some examples. And really reading some characters that I didn't know how it was doing it. Through proper training, I was able to reliably read those where it would have taken months to try and get an OCR Max or a traditional tool to read those. If you ever struggled with an OCR application, ViDi software and deep learning from Cognex is truly amazing in what it can read. Here's a simple example of where to use traditional machine vision versus deep learning. If we want to measure the length of a screw, this task is pretty straightforward using machine vision or traditional machine vision tools. If we want to measure the length of a screw, this task is relatively easy to automate using traditional machine vision tools. And it's more repeatable and faster than a human. However, if we wanted to look at this same part for defects, this is a task humans can do pretty well, but doing this over long periods of time leads to fatigue and inconsistent results. By trying to do this with traditional machine vision tools, it's proven to be difficult to automate. Where I mean the process of selecting the right vision tools and optimizing the parameters and getting it to actually pick up the defects becomes complicated. It can take a while to program these. This is an ideal target application for deep learning. The process simply requires you to collect a sufficient set of good and defective images, label them correctly, and then train the neural network. So the exciting thing about this deep learning algorithms and what it's capable to do is Cognex has now introduced this on the Insight platform, where we get the best of both worlds. A full toolbox of traditional vision tools, your measurement tools, your PatMax tools, your barcode reading tools, plus 3 new deep learning tools called ViDi Check, ViDi Detect, and ViDi Read. These tools operate in the familiar environment of the Insight cameras, and accessing the results is as simple as clicking a couple of buttons in the menu. With the new Insight D900, you do still need to use a GPU-enabled PC to initially train the neural network. So we have to have a computer or a laptop with enough horsepower to do the training. However, once we've done that, the algorithms are fairly simple. It's just a bunch of math that's running on the Insight standalone platform. The computer is no longer required. Earlier, I mentioned companies like Google can classify an image in amazingly fast time, like a millisecond. With the D900, you should be targeting applications in the 1 to 200 parts per minute range. We're fast, but we're not that fast. So let's take a closer look at applications for each of these deep learning tools. So ViDi Check is ideal for assembly verification applications. For things like kits, we're dealing with challenges like skews or rotated parts, packing reflections, slight variations in what the parts look like. Here we have a case where the same type of chocolate differs in appearance, so we can use a traditional tool like a PatMax tool because the stripes on the top vary in both quantity and location. We can't use a PatMax tool. But with deep learning, the system can learn to classify all of these variations as one common type. So whether the chocolate with the stripes on it has 2 or 3, as long as they're straight stripes, the ViDi tool learns that that's a certain type of chocolate. Here's another instance where deep learning outperforms traditional methods. This was an application or a representation of an application where we tried this with PatMax, and PatMax performed very well. So right now, we're just showing the results from a PatMax tool, trying to find all of these cutting tools. And as you can see, especially at the edge of the paper or what's meant to be packaging, there's a column there where it doesn't pick up all the cutting tools. If you notice the one labeled 45, it's hard to see with the eye, but we still pick it up. But it's on the edge of where we can reliably pick it up. So when we use deep learning, we simply get better results and more consistent results. So this image shows the results from deep learning. So even with all of that reflection and covering up the pattern that we're looking for, deep learning is able to find all of these parts. ViDi Detect is targeted at a wide range of defect detection applications and is particularly good at finding defects on metallic parts and grainy surfaces. For instance, anything in the textile industry looking for defects in stitching and patterns was an application that we always, were very reluctant to go after just because they were they were extremely difficult. The variation you would see in the patterns and the stitching made it extremely difficult for traditional vision tools to pick up. But now textiles with deep learning, it's a whole new market that we can tackle applications from. As a bit of an aside, when I first went to the Cognex corporate office, all the wood doors that they had there were painted black. When I asked about this, I got the answer, wood is no good. It's basically the attitude of the person that was walking me around, one of the managers at the time, that inspecting wood or other natural products was outside the domain for machine vision. It was a good place to lose money trying to solve really hard problems. Nothing really worked before, but now with deep learning, we're having a lot of success in these type of applications. So ViDi Detect can also find very small print defects. There are other tools that in the traditional Cognex Insight library, such as surface flaw, flexible flaw detect, that might be able to pick up some of these defects. But deep learning simply works better. And you don't need to try and optimize a bunch of complex parameters. If anybody's ever tried to use surface flaw or flexible flaw detect, they work really well, but there's a lot of parameters and a lot of back and forth and trying to figure out what's going to work the best. With ViDi, we just need to label these defects as good or bad and train them, and we get the results out that we're looking for. Lastly, ViDi Read. It's the perfect for OCR application. It's an area where I think you're going to find a lot of opportunities for the Insight D900. If you've ever tried to tackle an OCR application, especially a challenging one, the OCR Max tool is a great tool, but there's only so much it can do. You might be tempted to ask why you wouldn't just use ViDi Read for all OCR applications. That's a great question. There are two areas where OCR Max may be a better choice. First off is the line speed consideration. OCR Max in the traditional vision tool is more than 10 times faster than ViDi Read. So for applications above that 200 parts per minute, we may still have to use OCR Max. The second is form factor. Since ViDi Read is currently only available on the D900, the largest family or hardware platform Cognex offers, if you need something smaller, we may have to look at the traditional vision tools. Before we wrap up, I want to say a few more words about the training processes for deep learning. One of the most common questions people ask about the training is how long does it take, or things like what's normal, or is there a rule of thumb? Unfortunately, it's not at all that predictable, since there are several contributing factors, starting with the number of images. It's possible to train a neural network with a handful of images, 10, 15, but we've also had to do applications that required over 2,000 images. So the number of images, the size of the feature you're looking for. So if we're trying to to read characters that are small within the image or pick up really tiny defects, that may take longer to process. The image resolution. If we're looking at a 12 megapixel image versus an SVA or a 0.3 megapixel image, there's going to be a difference there. If we're looking at complex, hard to read characters on a consistent background, that's probably going to be easier than trying to do it on a background that's really confusing and complex. It also depends on the GPU that's in the computer that you're training. So, the standard laptop that I would use, I can train a neural network on it. I can train, VidiTool, but, it may take a day. With a low-end GPU, it may take 10, 15 minutes. With a GPU, an equivalent or a higher horsepower GPU, it may take one. So it depends on what kind of horsepower we're working with for this training. And you also need to consider the iterations. So if we need to look at those images 10 times, it's going to train quicker than if we need to look at those images 5 times. There's also, in the setup and the parameters for training, what Cognex calls perturbations. So we can artificially introduce some rotation, some contrast change, scale change to those features that we're trying to find, so that the software takes care of introducing those variations during the train process. The more variations we introduce in that train process, the longer it's going to take. But the one thing I really kind of want to point out here is, as we're doing this training, the time that it's going to take, it doesn't really take somebody who's familiar with machine vision. It's not somebody who's familiar with programming in C# or Java or Visual Basic. Really, it requires somebody who understands what those defects are, what they look like, what constitutes a good part versus a bad part. And they have to be diligent in making sure that we label those images and those features correctly. All right, so as we wrap up here, some key takeaways for you to think about as you assess deep learning. First and foremost, deep learning tools don't give you a free pass on the traditional fundamentals of machine vision. You still have to make sure you have good image formation, good lighting, good optics. We still have to make sure that the image is consistent and its quality. We can't take a shortcut on this. Second, and something that I can't mention enough, is that image collection and proper labeling is essential. If you make a mistake when labeling your images, you will in effect confuse the neural network. In the case of our houses, if we feed in a training image in an apartment but call it a house, the network will be trained to consider that apartment as a house, and that adds confusion. So in that case of defect detection, having a domain expert who can truly classify anomalies as defects is very useful. It is worth mentioning here that there's a process called bootstrapping, which is a bit of a shortcut in the labeling process. With bootstrapping, you can start by training on a subset of your images and then let the network classify the remainder. For instance, with the VidiRead tool, it comes with a pre-trained library of characters. So out of the box, it may read 90% of your characters without training. It may read 50, it may read 90. But you can label a small subset of those images, train the network, and have it tell you what it thinks those images are. And then it's much quicker to go through and verify what those characters are labeled to make sure that they are correct, rather than going through and manually labeling each one. So this process of iterative bootstrapping can really speed up your processing or your training time. Lastly is patience. If you attempt to shortcut the process, you'll likely fail. When you first get started with a feasibility study for an application, if your initial results are in the 80% plus range, don't be discouraged. This is pretty common, and anything above 80% is good. It's okay to start with a small set of images, say 50 to 75, just for a sanity check. but you may ultimately need 500 or 1,000 images, 500 to 1,000 images to get robust results. And finally, deep learning tools are not like Cognex. You don't get instant gratification when you click the train button. It's going to take some time. Consider that planning that time into your project workflow. We all start machine vision applications. We know what the defects or the criteria of the application are, and we program, we train for those defects, and you're always going to find more. Some new defect, some variation will show up. And with deep learning, we have to take those examples or those images of the new defects or the variations that we see and feed them back into the training process. So the training process is not a one and done. Depending on the complexity of the application, you might get away with one and done. It might take 2, 3, 4, who knows how many times to retrain and gather all of those new defect types that you're going to see. Deep learning will find them, but we have to be able to show us some sort of examples of what those defects look like. You know, if we taught the child what a house is, but we never explain, what a barn is, they may never know what that is. So the same thing with deep learning. So that kind of wraps up the presentation. I will check the chat window to see if there's anything else. And the other question, I guess, was just about classifying images as good or bad. Yes, depending on the tool, specifically with ViDi Detect, that's really all that's required, is you just label the image as good or bad. If you're doing the assembly verification, all we have to do is label the feature as what type of feature, what type of chocolate it is in the box. If we're trying to do the ViDi read, we just have to make sure that the labels that the software picks, especially when doing bootstrapping, are correct. We have to be diligent about making sure that that's correct. So if you've got alphanumeric characters, you have to make sure that all the zeros are labeled as zeros and none of them are labeled as D's or O's. So it's a more of a process of just double checking and being accurate in what you're doing. But the beauty of it is it doesn't require somebody who is an expert in machine vision or who is an expert in computer programming. It just requires somebody who understands what these defects are and what the application is trying to do as a total result. All right, and if there are any other questions, please raise your hand. Otherwise, I think that kind of wraps up what we wanted to present today. Thank you all again very much for joining in today. If you have any questions, you have my contact information, or reach out to your local tri-phase sales engineer. Thank you all very much. Have a good day.